a free response question for from 2002, and this one deals with the idea of impulse and conservation momentum, so something we're starting to look at. And it also has some calculus in it. So this is one of the harder examples, so I thought I'd walk you through it. So you've got a crash test car of mass 1,000 grams, moves at a constant speed of 12 meters per second, collides completely inelastically. When we say inelastically, there's that energy loss, and also we've got objects sticking together. With an object of mass m at time t equals 0, the object was initially at rest. The speed v in meters per second of the car-object system after the collision is given as a function of time by the expression. And the first thing we want to do is calculate the mass m of the object. So, in all collisions, whether they are elastic, partially elastic, or completely inelastic, momentum is always conserved. Because momentum is always conserved, you need to be really diligent in stating that in any solution. 9 times out of 10, just writing this or writing the statement, momentum is conserved, will get you a point on the AP free response. So now what I did is I went ahead and I set up what was my initial momentum. So momentum is mass times velocity, so the mass of the car and its velocity initially, plus the object wasn't moving, so we have a mass or a momentum of 0 initially for that. So my total momentum on this side is that 12,000 kilograms times meters per second. The final momentum of the system is going to be the 1,000 kilograms of the car plus that mass of the object times the velocity, and in this case it's that velocity function. Okay, and this happens, this collision happens, this transfer of momentum happens when time equals 0, and so we substitute in t equals 0 here in order to get our velocity, which ends up being 8 meters per second then. And so then we are able to go through and solve algebraically and find that the mass of the object is 500 kilograms. For part B, we're saying, assuming the initial position of x equals 0, determine an expression for the position of the car-object system after the collision as a function of time. So this is where the calculus starts coming in. So if you remember, velocity is the derivative of position. So to find a position function, we're going to have to integrate the velocity function. So I go ahead and I set x equal to the integral of our velocity function dt, because we are asked to do it as a function of time. And so then I substitute in my velocity function, and I'm going to then use substitution. So I'm going to say let u equal 1 plus 5t, and I have to take the derivative of that, so du is 5 dt. And I go ahead and I put that back in and I pull out my constants, so that x equals 8 over 5 and the integral of du over u, which is the same as 1 over u times du. The integral of 1 over u, or 1 over x, if you want to look at it that way, is the natural log. And because I have an indefinite integral here, I have to remember to add that constant c in. And so then I substitute in my u value back into my function to get 1 plus 5t there. Now, we're told that at t equals 0, x equals 0, and so then that means that our constant value is 0. So we can drop out that c, and we get a position function of 8/5 times the natural log of 1 plus 5t. Okay? And part C says determine an expression for the resisting force of an object-car system after the collision as a function of time. And so now we need to look at, going back to Newton's second law, F equals ma, it's kind of your bread and butter of Newtonian mechanics. We know that acceleration, which we have to be able to find, is the derivative of velocity. So I'm going to go ahead and take the derivative of my velocity function. Because this is a quotient, I then need to use the quotient rule, which I did right here, so you can see my work over here, and I plug that back in. So I find my velocity function to be negative 40 divided by the quantity 1 plus 5t squared. And I'm also looking at the mass of the total mass of the system. So I know that's 1,500 kilograms, the 1,000 from the car, and the 500 that I found in Part A. So I'm going to go ahead and now plug that into F equals ma, and I find my resisting force right there. Okay? Part D asks you to determine the impulse delivered to the car object system. So you can go about this in two different ways, and I wanted to demonstrate both of them. Okay? Impulse is equal to the integral of force dt. If you have a constant force, then it can be force times t. But in this case, our force is a function, so it's not constant. The other way you can do this is to say that the impulse is equal to the change in momentum. So if you look at the change in momentum side of my work, it's shorter, so I'm going to walk you through that first. Change in momentum is going to equal mass, because that's constant, times the change in velocity. And I'm looking at the impulse from 0 to 2 seconds. So I need the velocity at 2 seconds and the velocity at 0 seconds. So I just take my velocity functions and plug in my values here, and I find that the impulse is negative 10,909 kilograms times meters per second. You could also use, instead for these units, you could have also said newtons times seconds. It's the same thing, and both are acceptable. If you looked at it in terms of integration, here you're going to take a definite integral from 0 to 2, and I plugged in my force function, dt. Again, I've got to use substitution here, so u is equal to 1 plus 5t, and du is still equal to 5 dt. I'm going to pull out my constants again, just like I did before, and now I'm integrating from 0 to 2, du over u squared. Okay? The integral of 1 over u squared is negative 1 over u, and then I substitute my function back in for u, and I just go ahead and plug in my values, take the difference, and you'll find that you get the exact same answer no matter which method you use. So a little bit more of a challenging problem. I hope that this example gave you some insight. I felt the concepts were covered well within the lesson. But if you have any conceptual questions, by all means, let me know. I can make another video. I can answer them personally. You can put them up on our class discussion board to ask questions.